Morning everyone, welcome to my channel. In today's video, we will learn the types of gas turbines, the construction, and the operating principles of the different types of gas turbine. So we learn the single shaft gas turbine, double shaft gas turbine. We'll learn also the differences between the construction and the operating principles of single shaft and double shaft gas turbine. We will learn also the pros or advantages and cons or disadvantages of single shaft gas turbine and double shaft gas turbine. So let's get started. Discussion for week number 6. So video discussion. So I will record video for this discussion. So this is the continuation of the topic number 5, which is week 5, the types of gas turbines. What is single shaft turbine and double shaft turbine? Single shaft turbines are those which have single shaft running through the whole turbine, means through compressor, turbine, and generator gas turbine. So later I will show you the diagram or the drawing which illustrates what is single shaft turbines. The working of such a turbine starts with introduction of air in compressor section of turbine, which has blades to compress the air. So compressor. That compressed air then moves to the combustion chamber of the turbine, where it gets mixed with the fuel and burned to produce high temperature and high pressure gases. Those high pressure and high temperature gases then moves to turbine power generation section, where power is extracted from the hot gases by the blades of the turbine. Blades use the hot gases power to rotate the shaft of the generator or pump to produce the mechanical or electrical power output. All these rotating components like compressor, turbine, and generator are made on single shaft. So that is called single shaft turbine. So in here, this is the drawing of the single shaft turbine. So as you can see here in the drawing, we have here the compressor. So this is compressor. So compressor. And we have here the combustion chamber. We have here the turbine. So why it is called single shaft? Based on uh, the statement that we read. So from the compressor to the turbine and to the generator has only one shaft. As you can see here. So to the turbine and to the generator has only one shaft. So this is called single shaft. So from the word single is only one. So that is single shaft turbine. So we'll proceed to the double shaft turbine. So these turbines have two shafts. Remember, two shafts. In their system, where one shaft moves between compressor and compressor turbine, and the second shaft moves between power turbine and generator of gas turbine. Working procedure of these shafts is little different from single shaft turbines, and it starts with the introduction of air in the compressor section of turbine, which has blades to compress the air. That compressed air then moves to the combustion chamber of the turbine, where it gets mixed with the fuel and burned to produce high temperature and high pressure gases. Those high pressure and high temperature gases then moves to compression turbine section, and from there they move to turbine power generation section, which absorb power from gases. Power is used to rotate the shaft of the power turbine, and that shaft is attached. So this is shaft. Just a mistake. So I will attach with a generator which produce electrical or mechanical output. So I'll just make a correction. This one. This is shaft. So we'll see the diagram of the double shaft gas turbine. So this is the diagram of the double shaft or two shaft. So as you can see here, the shaft is separated. So before it was so I will, so this is your, so this is the two shaft or double shaft. So this is your compressor. And you have air compressor and you have turbine compressor. So you have air compressor turbine. So this one. And you have here the power turbine. So in double shaft turbine, as you can see here, drive shaft is only connected from the air compressor to the compressor turbine. So this is the first shaft. So on the second shaft, so they are not directly connected, no? So the second shaft, this is second shaft. Is separated and it is connected to the power turbine and to the generator. So they are separated. They are not. They are not like, or they are unlike. Not like to the single shaft, which is the shaft connected to the compressor and to the turbine and to the generator directly. But in a double shaft, they are separated. So the first shaft is connected from the air compressor to the compressor turbine, and the second shaft is connected to the power turbine to the generator. So they are separate. So there is no compressor turbine in a single shaft. But here in the double shaft or the two shaft, there is a compressor turbine and there is a power turbine. So the compressor turbine and the power turbine are separated, while in the single shaft, there is no compressor turbine and there is no power turbine. There are only compressor and turbine, and the shaft is common, which is single shaft. It is connected in the air compressor to the turbine and directly to the generator. So that is the difference of the single shaft and the double shaft gas turbine. So as I explained, the differences between the construction and the operating principle of single shaft and the double shaft gas turbine. So single shaft gas turbines are usually limited to generator drive applications, since the starting turbine load is significantly lower for generator application, because a generator is started under zero load. So while the double shaft turbines are used for mechanical drive, pump, and compressor application. So remember the application. Remember, if single shaft gas turbine, so if single shaft gas turbine, the application is limited limited to generator. So application. Okay. While the double shaft turbines are used for mechanical drive, pump, and compressor application. So those are the application of the single shaft gas turbines and double shaft gas turbines. So we have here the advantages and disadvantages. So we have also here additional information, uh, which is triple gas turbine. So uh, so here is the single shaft gas turbine, the double shaft or the dual shaft gas turbine, and the triple shaft gas turbine. So as you notice here, in the single shaft, you have only one shaft, you see, and the compressor and the turbine and the load, which is generator. So this is load. Is connected in just one shaft, you see. So one shaft. While in a double shaft or dual shaft generator, they are separate, you see. So this is they are separate in here, you see. So the shaft is separated in here. So here is the compressor. So you have here is the power turbine. So they are separated in two shafts. So first shaft is here, you see. So first, and here is the second shaft. So we have here the triple shaft gas turbine. So as you can see here, you have they are separated. So you have here also the shop, you see, this area. So in triple shop, the first shop and the second shop is connected. So you have here the second one and the third one. So this is load. They are different. So here we have the advantages and disadvantages. For the single shop, we have the advantages, which is simple design, lower maintenance, and we have here the disadvantages, requires large starting device, limited speed range, and lower efficiency. So those are the advantages and disadvantages of single shaft gas turbine. In the dual shaft gas turbine or the double shaft, you have here the advantages: higher efficiency, large speed range, requires smaller starting device, and we have also the disadvantages, which is more complex control system and higher maintenance. For the triple shaft gas turbine, we have here the advantages: high efficiency, large speed range, requires smaller starting device than one shaft, and we have also the disadvantages, which are most complex control system and higher maintenance. So we will talk about the fundamental, which is the gas turbine is working by the principle of Brayton cycle. So as we know, in the thermodynamics, Brayton cycle, these are the basic diagram. So in a Brayton cycle, we have here. So I already discussed this one in my previous video, but anyway, we have to explain this illustration. So in a Brayton cycle, there are, so first we have to tackle this simple diagram, which is open cycle. So this is open cycle gas turbine. So this is basic. So GT is gas turbine. So we have here the fresh air, which is coming from atmosphere and discharge also to atmosphere. So ATM is atmosphere. It's not at this moment. So there is a suction of the air in this area from the atmosphere, and it is compressed here in the compressor. So the pressure, it is compressed. So fuel is added here to the combustion chamber and it is ignited to create combustion. So after the combustion, it is the combustion gases is flowing to the turbine. So here, and it will cause to rotate the turbine blade and to rotate the compressor and the load here. So that is open cycle gas turbine, a simple gas turbine. So it is taken from Brayton cycle. So here, from 1 to 2, so from 1 to 2, here, so this is 1 to 2. So from here to there, it is called air, or it is isentropic process, no heat exchange. So the air is compressed. So here is intake, air inlet. So from 1 is inlet, so air inlet. And here is number 2 is compression. Compression. And this is called isentropic process from 1 to 2. And then from 2 to 3 is a combustion or heating, or the isobaric process at constant pressure. So as you can see here, this is PV diagram, the pressure is constant. You see this is single line, you see here. 2 to 3 is a single line. So in our PV diagram here, it is starts here. So the pressure is here, this area, and the volume is here. So the pressure is constant. So that is what we call the heat added. So 2 to 3 is heat added. So heat added here, Qn is heat added. Because of the ignition and the combustion occur. And then 3 to 4 is the expansion over turbine, which is isentropic process. So expansion means power. So 3 to 4 is power. And 4 to 1 is heat is rejected into the atmosphere in open cycle. So 4 to 1. So 4 to 1 here. So this is 3 to 4. And 4 to 1. So going there is heat rejected, or in other words, this is exhaust. So that is exhaust, or Q out is heat rejected, and Q in is heat added, or Q out is exhaust. So exhaust is heat rejected. So that is the explanation of the PV diagram using the PV diagram of the Brayton cycle, which applied to the gas turbine. So we have here also the TS diagram, or the temperature entropy diagram. So temperature entropy diagram. So as you can see here, the pressure is constant from, so first we have to discuss the position 1 to 2 here, which is intake and compression, and 2 to 3 is power. So and this is opposite in the no, not power, this is constant, the pressure is constant. So 2 to 3 pressure is constant, so the same here in the PV diagram. But the temperature, this is pertaining to the temperature, see. So 2 to 3, the temperature is rising. So temperature is not constant, you see. Please, if you graph here, so that the temperature is rising there, rising to there. And 3 to 4, the temperature is going down, you see. So temperature, if you graph here, from here to there, temperature is decreasing. And 4 to 1, the temperature is decreasing. So from here to there. So that is the temperature entropy diagram in the application of the gas turbine. Working principle. So working principle is the working fluid is initially compressed in the compressor. It is then heated in the combustion chamber. So this is just a review because I already discussed this many times. So finally it goes through the turbine. The turbine converts the energy of the gas into mechanical work. Part of this work is used to drive the compressor, and the remaining part is known as the network of the gas turbine. When examining the gas turbine cycle, we make a few assumptions. The working fluid is a perfect gas. The kinetic potential energy of working fluid does not vary along the gas turbine. Finally, pressure losses, chemical losses, and other kinds of losses are ignored. Variant. Closed Brayton cycle. So in a closed, this is closed cycle of gas turbine. So a closed Brayton cycle recirculates the working fluid, the air expelled from the turbine as reintroduced into the compressor. The cycle uses a heat exchanger to heat the working fluid instead of an internal combustion chamber. The closed Brayton cycle is used, for example, in a closed gas turbine and space power generation. So, although I already discussed this one before, but I will show you an illustration. So I will draw here. So in a closed cycle, we have here the so this is combustion chamber. So combustion chamber. So this is combustion chamber, and this is compressor. This is turbine. So why this is closed called closed cycle? Because there is a intercooler here, and exhaust gas here is recirculated or reintroduced to the compressor. So this is exhaust gas here. Reintroduced to compressor. Again, it is circulated to the combustion chamber and to the gas turbine. So this is called closed Brayton cycle. So as I said before, we have here the isobaric process. Isobaric process, the compressed air then runs through a combustion chamber where the fuel is burned, heating that air, a constant pressure process since the chamber is open to flow in and so next is isentropic process. So I will draw. So I will just draw here a small diagram. So compressor, turbine, combustion chamber. So isobaric process, the compressor runs through a combustion chamber where fuel is burned, heating that air. So from here, this area here is isobaric process. See, arrow. And the next one is isentropic process. The air is heated, pressurized, and gives up its energy expanding through a turbine or series of turbines. Some of the work extracted by the turbine is used to drive the compressor. So here, this area is isentropic process, the Brayton cycle. And isobaric process, closed cycle gas turbine or heat rejection to the atmosphere, closed cycle. So in the closed cycle, this is recirculated, you see. The exhaust gas is reintroduced to the compressor. So here is isentropic process, ambient air is drawn into the compressor where it is pressurized. So this area. There. So that is isobaric process. Classification. We have gas turbine, path of working substance. We have a closed cycle gas turbine, open cycle gas turbine, semi-closed cycle gas turbine. So we have also gas turbine process of heat absorption, constant pressure gas turbines, and constant volume gas turbines. Ideal gas turbine cycle, closed Brayton cycle. So we have we already discussed this diagram. So you just review or rewind the video. So this one is the same. This one is the compressor, you see. Right, so the same heater. So heat source. We have so this is closed cycle. If you can see, this circuit is closed. The line is closed. This is closed cycle. So work done by the turbine per kilogram of air. So in this diagram we already discussed. So what we have here, the equation, work done is equal to, here we have here the C, which is constant pressure. So this is the formula. Work done. So work done mass multiplied by the constant specific heat at constant pressure multiplied by the change in temperature. So T1, T3 minus T4 is change in temperature or delta temperature, and CP is constant pressure, or we have here formula work done is equal to mass times the constant pressure multiplied by the delta temperature, which is T3 minus T4. So here. So we have here also the equation, work required by the compressor per kilogram of air. So by use of the PV diagram, we have here the work required, which is WC is equal to constant pressure multiplied by the delta temperature, or the T2 minus the T1. So work done is equal to mass times the specific heat at constant pressure multiplied by the change in temperature. We have here the network available in a gas turbine. So W is equal to WT multiplied by WC, or W is equal to constant pressure multiplied by delta temperature, which is T3 minus T4, minus the constant pressure multiplied by the temperature 1 minus temperature 2, or the delta temperature, or we have here the W, or work network available in the gas turbine is equal to constant pressure multiplied by so bracket multiplied by temperature 3 minus temperature 4 minus temperature 2 minus temperature 1. So for isentropic process, we have here the TS over TL is equal to P over PS over PL. So with this equation, so in scientific calculator, you have to click this symbol when applying the calculation. So multiplied by the y minus 1 over y. So these are the basic components. So we already discussed this one before. So just review our previous video. So that's this one, the basic components. So just put this one in your mind. These are the basic components of the gas turbine. So this one here. So of course this compressor draws air and compressed air. Combustion chamber. So here fuel pump and ignited to burn the compressed air. So here, this area. Turbine hot gas converted to work. So this area, and can drive compressor and external load. This area. So we have here the combustion chamber. See? So combustion chamber, fuel pump, and ignited to burn with compressed air. So this area. We have here the turbine. Hot gas is converted to work and drive compressor and external load. So this area. So compressor supplies high pressure air for combustion process. We have compressor types. We have radial and centrifugal flow compressor and axial flow compressor. Compressor, this is radial. Disadvantages, simple design, good for low compression ratios, 5:1. Disadvantages, difficult to stage, less efficient. For the axial flow, here, axial flow, good for high compression ratios, 20:1, most commonly used. Use of compressed air, primarily air is 30%, pass directly to the combustor for combustion process. Secondary is 65%, passes through the holes in the perforated inner seal and mixes with combustion gases. Film cooling air 5% insulates holes turbine blades. So these are the drawing for the blade cooling. Combustion chambers. So where air and fuel are mixed, ignited and burned, spark plugs used to ignite fuel. So we have the types: can for small, centrifugal C compressors, annular for larger, axial compressors. So can, annular rarely used. So it is a combination of the can and annular combustion chambers. Turbines consist of one or more stages designed to develop rotational energy, uses sets of nozzles and blades. So we have single shaft, power coupling on the same shaft as turbine. Same shaft drives a rotor of compressor and power components. So I just rewind this video because in the beginning of this video I already discussed. So just rewind for more information. Split shaft. So we have a split shaft or what we call the double shaft. So here, turbines, split shaft, gas generator turbines drives compressor. Power turbine, separate from a gas generator turbine. Power turbine, driven by exhaust gas from generator turbine. Power turbine drives power coupling. So split shaft or double shaft or dual shaft or double shaft or dual shaft. So we have here, you see the first shaft, and we have here the second shaft. The second shaft, you see. Second shaft. So split shaft. Dual shaft. So this one is the same. Split shaft and dual shaft. So improving turbine efficiency, we have the intercooler. So compressing the air into stages and using intercooler between the two. Reheating. So So actually the diagram of this system I already discussed before. So just for more information, just review my previous video. So reheating, expanding the air into two stages and using a reheater between the two. So other types. So semi-closed gas cycles turbines, combination of an open and closed cycle gas turbine, constant pressure gas turbines, air heated combustion chamber at constant pressure. So constant volume gas turbines, air heated and combustion chamber at constant volume. So we have air gas turbine, air system, air intakes are located high up and multiple filters, discharge, stacks. Fuel system uses this specification. Ignition system supply bearings to the gears with oil. Advantages of gas turbine: very high power to weight ratio, more size efficient, moves in one direction only with fewer moving parts, low operating pressures, high operation speeds, low lubricating oil cost and consumption. Disadvantages: of gas turbine engines. More expensive compared to a similar size reciprocating engine. More complex machining operations. Usually less efficient than reciprocating engines, especially at idle. Delayed response to changes in power settings. Comparison. Gas turbines versus steam turbines, gas turbines versus IC engines, closed cycle gas turbines versus open cycle gas turbines. So, any questions? You have questions? You write in the paper and you ask question to me during the virtual meeting discussion. So this is here is the end of the discussion. So I will end this video. So don't forget to like and share. Click subscribe so that you will be updated for the next video. And don't forget also to click the notification button. And see you on my next video.